Okay, last time we started the subject transmission matrix. And essentially what transmission matrix does is relates pressure and particle velocity at one field point to another set of variables at another position. Okay, and the matrix in matrix expression we write it as in terms of pressure units. Okay, and this is our transmission matrix. And we have elements. So the description, when you write the equations, we write them in terms of T11 P2 plus T12 rho C U2. The things to remember here are the variables, okay? Pressure and rho C times pressure. These are written for plane waves. And we express them in terms of, again, pressure and particle velocity at the second location. So once we know, for example, the transmission matrix for the space or for the field between the two positions, then you can always find what it is in one or the other as long as you know the values again on one or the other. And the importance of this comes in when you have a combined set. For example, you have a plate, and then you have a fluid and a membrane. Then you can write the equations for the plate, layer, membrane, and you'll be able to determine actually fairly easily the pressure and particle velocity beyond those media. Okay, and we derived these for normal incident waves. So do we have a volunteer who might do it, let's say, for a layer? Okay, just a layer, acoustic layer, in between two places for a sound wave that comes in an oblique direction. Okay, and what that means is sound wave transmitted obliquely. There is no change in fluid medium. There is no change in fluid medium. So there's no refraction. Okay? What is the transmission matrix for, let's say, between these 2 points? In free field, in this case, in free field, as sound propagates, what is the relationship between any 2 points for the variables? That's all. So if this were a wall and this were a wall, that would be a different transmission matrix. Then you have different boundary conditions. But right now, this is an open free field. And what you normally do is you write acoustic free field equations, assuming that waves can go back and forth, because we don't know. And then you find the pressure and velocity at one, you find the pressure velocity at the other, and you eliminate the coefficients to get the result. Okay? So to do that, what do we do? So for an oblique angle, what we do is, as Emre just mentioned, we write the, I'll drop the time harmonic, ik cosine theta x, and corresponding okay. And if we evaluate, let's say, pressure at position number 1, then we will write the expressions for position number 2. A plus B rho C U1 similarly. Oops, T. Okay. What we want to do is find A and B in terms of P2, U2, and substitute it back in here. Okay? If you do that, then you have this open relationship. As you can see from here, we can write the expression for B in terms of U2, and that gives us, oops. let's see. Okay. And you can see transmission matrix now is and how does it differ from the normal incidence case? Can you quickly see? Cosine theta, there's no other difference. What is the determinant? Can you do a quick calculation and find out what the determinant is? Yeah, as before. No energy is added or no energy is subtracted from the system. So the only difference in this case, as I mentioned before, is the oblique angle that seems to change the impedance slightly. Now, why don't you try the following? Do you have any questions on this, how this is derived? When you listen to it, it sounds simple, but when you start doing the actual derivation, sometimes you find it confusing. But do you have any questions? Okay. Now, if I ask you to do a simple one, can you do it? Okay. Why don't you find the transmission matrix through a fluid interface? Okay. Transmission matrix through it's not a layer, but fluid interface. So you have a boundary, you have row 1, C1, row 2, C2, and sound is coming at an angle theta. What would be the transmission matrix for this? This is simpler than that. Okay, why don't you help me? Okay? We want to find the transmission matrix through a fluid layer, through an interface of a fluid, from one fluid to the next. What does that mean? What are we trying to relate? We're trying to relate pressure and velocity on one to the pressure and velocity on the other. So what are we really speaking about is either side of the interface, correct? Pressure, velocity, pressure, velocity. We want to relate them. What do we know about them? What is it that we know?
We know boundary conditions.
Okay. What is the boundary condition? What are they?
Pressures and velocity must be continuous at the interface.
Okay. So Let's start with the pressure. Pressure must be continuous. Does that mean P1 is equal to P2 at, let's say, X, we'll call it X0? Everybody agree? Okay. What's the next?
And velocity must be continuous.
Okay.
There's no mass.
Would you say U1 is equal to U2?
Actually, rho 1 C1 U1 is equal to rho 2 C2 U2.
Really? Why?
I think impedance must be.
Continuity. Think about continuity. Go ahead.
Normal velocity.
Right. The normal velocity. Okay. So how would we express that? Normal to the surface. How would we express it?
Cosine theta.
Yeah. No, sine. Look at the angle. U1 cosine theta must be equal to U2 cosine theta. Oh, did you? Sorry. Okay, I'm sorry. I missed the co part, just heard the sine. Okay, now we're getting someplace. Okay? Remember now, the format that we use is okay. This is pretty straightforward. This is 1 and this is 0. You agree? Relationship between P1 and P2.
One of them is cosine instant, right?
Very good. Okay, what else are we missing? Okay, so this is all right. Now, what do we do here? And of course, that has to be taken into account as well. What we do here now is multiply rho 1 C1 cosine theta 1, say rho 1 C1 V2 cosine theta 2. So far we're okay. Now the next thing you do is to make sure it comes in the same format. We do need rho 2 C2 in front of it, but that means we should also divide it by rho 2 C2. Oop, there's a U1 here. And finally, to clean this up, that would be a transmission matrix element, and this would be 0. This is what you obtained? No? Okay. Not really? Okay. Okay, so for the layer, we would have 1, 0, 0, and rho 1 C1, rho 2 C2, cosine theta 1 divided by, sorry, theta 2. Let me see if that's what I have. Yep. Okay, when you try to do it, what was the problem? How far did you get? When you tried to do it, how far did you get?
I missed the boundary conditions to normal velocity.
Aha, okay. Normal value, yes. Once you have those, well, now that you know what to do here, we can ask you to do something just as simple. If you have a membrane, okay, and if you have an oblique angle coming at it, what would be the transmission matrix for it? Don't look at your notes from last time because we didn't do it that way. Just think about it. Let's just do it together, okay? What would you do? It's no different than the interface.
Just the pressure will not be continuous.
Pressure will not be continuous, okay? What will happen then?
It will cause the acceleration.
Okay, so how do we describe that? See, this is a membrane now. And we discussed last time that membrane basically acts like an inertia, a mass, okay? And so how would we express this? The membrane and its relationship to pressure.
Pressure difference is equal to mass times acceleration.
Right, you can do mass times acceleration, or similarly, impedance times the velocity, okay? Now, what else do we know?
And the velocity are continuous. Velocity is continuous.
Velocity is continuous. And how do we express that?
U1 cos U1 times cos theta I equal to U2 times cos theta.
Okay. This is the same fluid, so it will not matter. And how does that help here? You have the answer. Khan. How does this help here? It's what? It's the same as eta. It has to be. For continuity, the plate or the membrane velocity must be equal to the normal velocity of the particle on both sides. That's essentially it. So what you have here is P1 is equal to P2 plus eta, and U1 is equal to U2 U2 cosine theta. Thetas go out, and that's equal to zeta n. Okay, I guess, for generality, we're going to keep it this way. Cosine theta 2, cosine theta 1. Okay. Okay, so Okay. You have a question? Somebody? No? Okay. What we did is I added a couple of other variables here, okay? If the membrane is separating, just to make it more general, if the membrane is separating two fluids instead of the layers, because there's a purpose here that I'd like to express in a moment. Yes, okay. So let me write it in terms of the transmission matrix for the membrane. One normalized Okay, take a look at this membrane matrix, and then take a look at the matrix that we developed for a fluid layer. Not layer, sorry, fluid interface. Do you see any relationships? Do you see anything that's familiar? Okay. Remember, each time you look at these, it's supposed to tell you something. The components of transmission matrix, which come from these two equations. What is Z in this case? We can make it just membrane, just to make sure that, just membrane, yeah, it's not a big deal. Membrane impedance normalized with respect to the acoustic impedance of the second medium. This is the angle at which it's transmitted. Just a moment ago, we derived a very similar relationship, but without the membrane. Okay? If you take a look at this, and we say, let's take the membrane out, that means this would be equal to 0. When this is 0, you see exactly the other one. So these have to be naturally consistent, okay? So you can, what this tells me also is, I can probably replace this with a plate. Then I have a plate impedance here, and I have the same transmission matrix. Okay? In fact, when we study plates starting next hour, okay, you'll see that we'll be able to drive and replace it with that. As simple as that. In the other case, there was no inertial impedance, so we didn't have that. But the plate is going to be more than an inertial impedance. It will have stiffness, bending waves, vibration, how plate vibrations come into play. Okay, any questions on transmission matrices? I think for now, at least, that's what we will cover. And I probably will get you some homework problems on this to prepare you. Questions? Okay. 3-minute break. Okay.